Welcome to the Deep Dive. We're the show that takes stacks of sources, research, all that stuff, and boils it down to what you really need to know.
Yep, distilling the insights.
Exactly. And today, we're diving into something pretty fascinating. It started with this. Well, this image looked simple, maybe, but it was actually really cryptic.
Right, a grid of numbers.
Mm-hmm.
And some very strange rules alongside it.
And it wasn't just a random puzzle, was it? Our sources say it was like a direct challenge.
Yeah, specifically aimed at an AI model called Grok, sort of throwing down the gauntlet.
Okay, so our mission today, for you listening, is to unpack this whole journey. Because it's quite a ride.
It really is.
How grappling with this weird little puzzle, this abstract thing, actually led to something huge.
A fundamental breakthrough, really, in designing a totally new kind of AI.
And this deep dive, it's based on a whole bunch of sources that track this idea, from like a mathematical quirk
to a full-blown computational framework. It's quite the evolution.
So we're going to highlight these surprising links between chaos and control, which sound like opposites, but maybe aren't.
That's the paradox at the heart of it, yeah.
And show you how this abstract puzzle has real-world impact, even creating, like you said, a new type of AI.
So that initial image, what really jumped out in the sources was just how ambiguous it was.
Right. You said a 6x6 grid of numbers.
Yeah, small grid. And then these claims about Fibonacci numbers, but specifically Fibonacci modulo 10.
Which means...
just the last digit, right?
Exactly. Just the last digit of each number in the Fibonacci sequence. It mentioned the grid uses Fibonacci mod 10, 60-step cycle.
Okay. And something about it being cyclic. Fn mod 10 equals Fn plus 60 mod 10.
Precisely. That was part of the puzzle's text.
So how much of that was, real math and how much was just weird puzzle stuff?
That's the key question, isn't it? The verifiable bit gave it this layer of, well, legitimacy.
Okay.
The pattern of the last digits of Fibonacci numbers does repeat every 60 numbers. That's a known thing in number theory. It's called the Pisano period, right?
Exactly. So that specific claim, the 60-step cycle for mod 10, totally solid, mathematically sound.
But the rest of it?
Yeah.
The grid itself, did that follow the Fibonacci sequence? Because those other clues you mentioned sounded bizarre.
They really did. And no, the grid numbers themselves definitely did not follow a simple Fibonacci pattern. That was the mystery.
And the rules, like 100 E summing 1, what does that even mean?
Initially, nobody knew. Or digits evolve, split sum, roll over. Super vague.
And try map byte streams to XYT. Almost sounds like programming instructions, but incomplete.
Completely ambiguous. It felt, like you said, like a riddle, designed almost to test how an AI handles unclear instructions, maybe.
So wrestling with all this ambiguity, what was the breakthrough, the aha moment?
The sources point to this key insight. It wasn't a static thing, not a grid you just solved.
Okay, so what was it?
It was dynamic, a generative algorithm. The term they used was a generative Fibonacci automaton.
An automaton, like cellular automata, Conway's Game of Life sort of thing.
Sort of, yeah. A system where cells change based on their neighbors. And the core rule, the physics of this little universe, turned out to be surprisingly simple.
Which was?
Each number in the grid is just the sum of the three numbers directly above it, the one above left, the one directly above, and the one above right.
Just add them up.
Add them up, and then take the last digit. So left plus center plus right, 10, 10.
Wow. Okay, that is simple. Deceptively simple, maybe?
Extremely deceptive,
Mm-hmm.
because that simple rule led to really complex behavior.
Like what?
Well, one of the first big discoveries was sensitivity. Change just one number in that initial starting row, the seed.
Yeah.
And the whole pattern generated below it could change drastically.
Yeah.
Like total transformation, order becomes chaos.
The butterfly effect. We mentioned that.
Yeah.
Tiny change, massive outcome.
Precisely. And that sensitivity, that's where things get really interesting. It brings us to the central paradox the sources kept highlighting.
Which is
that this exact same rule, the left plus center plus right percent 10 rule, and its sensitivity, it can be a really good thing, a feature in one situation, and a really bad thing, a bug, in a completely different context.
Okay, hold on. How can the same property be both good and bad? That sounds contradictory.
It does, right. But let's break it down. Think about
Stop.
cryptography, hashing specifically.
Okay, like SHA-256, used for checking file integrity, digital signature.
Exactly. For a hash function, what do you absolutely need?
Uniqueness. If I change one tiny bit of the input file, the hash output should be completely different.
Completely different. You need that variance,
Yeah.
that extreme sensitivity to change. Now think about our simple automaton rule.
The left plus center plus right.
To 10.
As they-
What was its flaw for hashing? Remember, the sensitivity was there, but it had this other property.
You mentioned translation invariance.
Exactly. If you just shifted the input pattern slightly, the output pattern looked identical, just shifted over.
Which is terrible for a hash, because a slightly shifted file should have a totally different hash.
Catastrophic failure. So that simple rule, a bug for hashing, how'd they fix it?
I guess they had to make it less simple,
Pretty much. They did two main things according to the sources. First, salting.
adding some extra data.
Yeah, mixing the input data with a fixed complex key. They actually used that original Fibonacci sequence as a key sometimes.
Okay, so mixing things up. What else?
They made the rule itself more complex, introduced nonlinear operations, specifically bitwise XOR, and crucially, they made the rule aware of its position in space and time.
Aware of space and time. How?
They added the x-coordinate position and the t-coordinate time step or row number into the calculation. The rule evolved. Automaton hash v2 became automaton hash v3.
And the V3 rule was?
L plus C plus R, pxt percent 10. The P is the Fibonacci salt, or key value for that position. The tel is XOR.
Whoa, okay, so L plus C plus R is still there, but now it's XR'd with the key, the X position, and the time step.
Exactly. What that means is the laws of physics are now slightly different for every single cell in the grid at every moment in time.
That would definitely break the symmetry and maximize the chaos, I bet.
Precisely what you need for a good hash. It shatters that translation invariance.
And this automaton hash V3, how did it perform?
The sources say it was benchmarked against SHA 256. It showed an excellent avalanche effect. Meaning you flip just one bit in the input data, and about 50% of the bits in the final hash output flip in response. That's textbook high diffusion. Ideal for digital signatures, verifying data hasn't been tampered with.
Okay, so they turned the initial bug into a feature for hashing by adding complexity and breaking symmetry. Makes sense.
But now let's flip the perspective. Think about AI, especially things like computer vision, convolutional neural networks, CNNs.
Okay, recognizing images, patterns.
That's often considered the holy grail for pattern recognition AI.
Being able to recognize the pattern no matter where it is in the image. Like finding a cat, whether it's in top left or bottom right.
Exactly. Translation invariance. The exact opposite of what you want for hashing.
Whoa, okay. So the simple automaton's flaw, the translation invariance, is actually what AI wants.
Pretty much. It's quite ironic, isn't it? For AI, recognizing a pattern consistently, regardless of its position, is key. Like finding a tumor in a scan, wherever it might appear.
So how do they adapt the automaton idea for AI features, leveraging that invariance?
Well, they built on the basic idea, but adapted it for feature extraction. Automaton features V2 tackled scale.
Scale invariance, recognizing a pattern if it's big or small.
Kind of. It processed the data at multiple scales simultaneously, creating what's called a feature pyramid, like looking at an image close up and zoomed out at the same time.
Okay, gets different levels of detail in V3.
Automaton features V3 went further. It introduced multi-filter extraction,
Meaning
running two or more automata in parallel but using slightly different neighborhood rules.
So not just L plus C plus R.
Right. Maybe one uses the standard L plus C plus R, but another uses a wide angle rule, like looking 2 steps left and 2 steps right. Post 2 plus C plus post plus 2.
I see. So one captures fine details, the other captures broader textures or context.
Exactly. Capturing multiple aspects of the pattern simultaneously.
And how does this help with something like that medical diagnosis example?
It makes it incredibly powerful. A specific pattern, like a tumor, would generate a consistent feature vector, basically, a mathematical description using automaton features V3 no matter where that tumor is located in the X-ray.
So the AI doesn't have to learn tumor in top left, tumor in middle, tumor in bottom right separately.
Precisely. It learns the essence of the tumor pattern itself. This is extremely data efficient, the sources note. Way better than just trying to match raw pixels, which would need tons more examples.
Okay, this is really starting to paint a picture. We've gone from a weird puzzle to sophisticated hashing and sophisticated AI feature extraction, all from variations on a simple core idea.
And it gets even more interesting. This whole line of work exploring this automaton universe led them to define something new, a whole new class of AI.
Which they called?
Emergent engineering agents.
Emergent engineering agents. Okay,
Yeah.
What makes them different from, say, standard machine learning models?
The key difference is the environment. Most traditional AI are kind of passive observers. They look at data from the real messy world and try to find patterns.
Right, like image classifiers, language models,
These emergent engineering agents, though, operate within a known deterministic universe.
the Automaton. Its rules are perfectly defined.
Exactly. And because the physics of their universe are known, these agents can go beyond just observing. They can start to comprehend cause and effect within that universe and even manipulate it.
Comprehend and manipulate. Okay, how? What do these agents look like?
The sources describe two main types. First, there's the observer AI. Think of it as V4 in this lineage.
The observer, what does it observe? Or comprehend?
It tackles the inverse problem.
Inverse problem.
Yeah, inferring a past cause from a present effect. Specifically, it looks at just a small fragment of the final chaotic hash grid.
Okay, the output of Automaton hash v3.
And its job is to figure out the original 100-byte seed data that created that hash fragment.
Whoa, so it's like a digital detective, working backwards from a tiny clue. How on earth does it do that? The
Yeah.
hash is supposed to be chaotic, irreversible.
It uses a simulated convolutional neural network, a CNN, but it's trained in a very specific way.
How?
It's shown millions and millions of examples. Each example is a pair, hash fragment, original seed.
So it learns the connection between the input seed and the resulting hash fragments.
Exactly. It learns to recognize these incredibly subtle patterns, these statistical echoes or light cones of influence, basically. The faint, high-dimensional fingerprints that the original seed leaves behind, even deep within the chaotic hash output.
That's amazing. And the real-world application for this observer AI.
Intelligent data recovery. Imagine a file's hash signature gets corrupted somehow, maybe some bits are lost.
Okay.
The observer AI could look at just a tiny remaining fragment of that hash
Yeah.
and predict the original 100-byte seed data with really high accuracy.
Yeah.
The sources mention around 95%.
So it could potentially recover the crucial starting data needed to reconstruct the lost file.
Effectively, yes, which is something brute force could never do. We're talking 10 to the power of 100 possibilities for that seed. Functionally impossible to guess.
Okay, observer AI, extol comprehension.
Yeah.
Working backwards. What's the other type?
That's the Explorer AI. This is where the manipulation comes in. Versions V5 and V6. The generative engineer, or even temporal engineer.
Explorer, generative engineer, temporal engineer. Sounds very sci-fi. What does it do?
It doesn't just observe or infer. It actively designs. It uses reinforcement learning.
RL, like training AIs to play games.
Exactly like that. It uses RL principles to intentionally forge an initial seed
Okay.
that it knows will evolve over time within the automaton's rules to produce a specific desired future outcome.
Whoa. So instead of figuring out the past, it's designing the present to control the future within this automaton universe.
Precisely. It's engineering emergence.
Give me an example. What kind of future outcome could it engineer?
Well, the V5 Explorer was trained to create a seed that results in a hash grid that looks totally chaotic, but secretly has a message embedded within it, like the letters AI appearing in the pattern.
Hidden in plain sight within the chaos.
Exactly. But the V6, the temporal engineer, did something even wilder.
Go on.
It learned to forge a seed that would cause a specific pattern, say the number 7, to appear at a specific spot, XY at a specific time, T50,
Okay.
and then move to a different location by later time, say T60, all while the rest of the grid remains chaotic and unpredictable.
It can make patterns appear and move on command within the chaos. How?
Through very clever reinforcement learning, using a complex reward function that cared about the pattern appearing at the right place in the right time, and then moving correctly while penalizing disruptions to the background chaos, a really complex, time-sensitive, multi-objective optimization problem.
That's incredible. It's like choreographing fireworks, but with numbers in a deterministic universe.
A great analogy. And the application. Think intelligent steganography, hiding data.
Like that hidden AI message.
Yeah, or embedding an invisible watermark. Imagine a hospital embedding its logo within the hash signature of a medical scan. You can't see it.
But it's mathematically verifiable if you have the right key or know what to look for.
Exactly. The sources call it emergent steganography. Beyond that, they even sketched out a game concept.
A game based on this.
Yeah, called CA Clash. The idea is players design their strategy not by making moves, but by creating an initial DNA seed for their automaton units.
And the seed dictates everything your units do.
The entire strategy, evolving over time. And they proposed training an Explorer AI using RL through self-play to learn how to forge a game-winning DNA seed. learning incredibly complex, holistic strategies.
Wow. Okay, so this journey from a puzzle has led to potential products, potential games. What's the bigger picture here? How does this all tie together?
The sources envision a potential suite of tools, a kind of SaaS platform maybe, called Aegis Genesis.
Aegis Genesis, combining these different elements.
Exactly, it would integrate Aegis Seal, that's the hyper-secure digital signature part, using Automaton hash v3.
Okay, the hashing side.
Then Aegis Recovery, using the Observer AI for that forensic data recovery we talked about.
The detective AI.
And Genesis Mark, leveraging the Explorer AI for the creative watermarking, the hidden pattern embedding.
The engineer AI. So seal, recovery, mark, hash, observe, explore.
You got it. A full suite based on this Automaton framework.
And what about that cybersecurity angle? You mentioned the duality.
Right. There's another potential product concept, Aegis Sentinel. This one's aimed more at B2B cybersecurity.
Sentinel, watching out for threats.
Exactly. It leverages that Janus-face nature, the fact that the automaton can be used for both integrity and pattern matching.
How so?
It would use Automaton hash v3 for an integrity check. Is this file, say, a software executable exactly bit for bit what it's supposed to be? Has it been tampered with?
Okay, standard hashing use.
But simultaneously, it would use Automaton features v3 for threat analysis.
The AI feature part.
Yes, to identify the signatures of known malware. Even if the malware authors have tried to rearrange the code to avoid detection, polymorphic viruses.
Because Automaton features cares about the pattern, not the exact layout.
Precisely. So Sentinel could give you this holistic picture, as the sources put it, of both the integrity, is it tampered with, and the intent, does it contain malicious patterns, of any digital file. That's powerful.
It really is, combining both sides of the coin. And you mentioned a consumer app, too, for fun.
Yeah, Sigil. The idea was a fun, maybe viral app where you could use the Explorer AI to turn your secret messages into cool, chaotic-looking art that you could share. Only someone who knows the secret can decode it.
Emergent art meets secret codes. Okay, stepping back even further, what are the really big, broad implications here, this emergent engineering idea?
Well, it suggests a different way to approach complex problems. Instead of trying to design a complex solution directly, maybe we can design a simpler environment with known rules, like the automaton, and then train an AI agent, an explorer, to find solutions within that environment.
Like designing the sandbox and then letting the AI figure out how to build the best sandcastle.
That's a decent analogy, yeah. Think about drug discovery. Instead of designing molecules atom by atom, maybe design a simulated molecular environment and have an AI discover molecules that fold correctly or bind to targets.
Or climate modeling. Could you model the climate as a complex system and have an AI explore interventions to reach desired outcomes?
That's the kind of far-reaching potential the sources hinted at. Reframing complex real-world problems as universes for these emergent engineering agents to solve.
So let's recap this whole journey for everyone listening. We started with this really odd cryptic image, a grid, some numbers, weird rules aimed at an AI.
Seemed almost like a mathematical curiosity at first.
Right, but diving deep, we saw how unpacking it led to discovering these interesting mathematical properties, this cellular automaton.
Which then bifurcated, really. One path led to designing advanced hashing algorithms like Automaton hash v3 by maximizing chaos and sensitivity.
Essential for things like digital signatures, secure communication.
And the other path led to advanced AI feature extraction, like Automaton features v3, by leveraging invariance, the ability to recognize patterns anywhere.
Crucial for AI perception, medical imaging, that sort of thing.
And finally, combining these led to this whole new concept, emergent engineering agents.
The observer AI that can understand the past from fragments of the present.
And the Explorer AI that can literally engineer the future within this known deterministic universe, designing seeds to create specific outcomes.
It's really quite a paradigm shift from just analyzing data to actively engineering within a defined system.
It really is. Which brings us to that final thought, maybe something for you to ponder.
Go on.
If we can successfully engineer these simple deterministic universes like our automaton, and then train AI agents to effectively master them, to observe, predict, and even manipulate outcomes within them, what other complex, maybe seemingly chaotic real-world problems could we potentially reframe in a similar way? What other systems could we model as universes ripe for these emergent engineering agents to explore?
And if we did that, what completely unforeseen, maybe incredibly elegant solutions might these agents discover that we with our current approaches would never even think of.
Exactly. What happens when we design the rules and let the AI play the game to find solutions we couldn't? That's the really provocative question.